It's a pleasure to present Renato Calleja from the Universidad Nacional Autonoma de México, Mathematics and Mechanics, IIMAS. And Renato will present the talk with title Some Choreographies of the N-body Problem and the Conjecture of Symmetry. Then it's a pleasure to receive Renato, and let's watch the talk. Thank you, Renato.
Thank you, Tiago, for the presentation. So it's really my pleasure to be here for Hildeberto's conference for his 80th birthday, and I want to talk about some ideas of choreographies that emerge from polygonal equilibria to the equations of the n-body problem in the rotating frame. So this is some work that I have been doing with several people. I put here the number of the name of Eusebius Doedel, my colleague Carlos García-Azpeitia, and there's some other people that joined to this project recently. Well, maybe 3 years ago already, which are Jean-Philippe Lessard from Marchal and Mireles James, and they are both experts in computer-assisted proofs. So I will say something about computer-assisted proofs towards the end of the talk. Well, thanks a lot for the invitation. Could you please pass the slide? So I want to talk about choreographies. So here I put the equations of motion of the n-body problem, right? And we're looking for some special kind of solutions, and we're talking about solutions where all the particles, we have n particles here, so all the particles are going to follow the same path, right? So we have j goes from 1 to n, right? And then all the particles are different instances for different times of the time of a just one second. Yes, of a curve. So so could you go to the previous slide? Yes. So we're thinking that yeah. So going from one particle to the other is like the effect of the Zn action acting on the curve, basically the circle. So the action is basically going from one particle to the next, right? So there's different delays for different particles along the curve, right? So then we go to the next slide, and then we see the first example, which is a very famous one from the 1700s. It's an example by Lagrange. And Lagrange found that for 3 equal masses, the particles, the 3 bodies can go on a circle. So it's a circular configuration. The particles are basically on an equilateral triangle. Okay, so that's the first, actually that's the first example of a choreographic solution, like the ones I was showing before, because all the particles are following the same curve, and the curve is a circle. Okay, could you go to the next slide? So now the idea of choreographies, there was a different idea of a choreography, and it started with the work of Chris Moore. So Chris Moore was basically doing numerical work. He was looking for braided solutions of the n-body problem, and then he found by minimizing, he found a solution that's basically the 3 bodies follow a figure-8 configuration, right? And then a few years later, without knowing about the numerical work of Moore, Alain Chanciner and Richard Montgomery, they proved the existence of the same solution, this is a figure-8 solution, and they did it by minimizing paths, going from connecting basically a collinear configuration with a triangular configuration, right? So then, of course, the problem, I mean, the proof was done by minimization techniques. And of course, the problem with the minimization techniques is that you have to avoid collision solutions, right? And so this was a good part of the work done by Schanziner and Montgomery. So later, there was work of Carles Simon, who did numerical work. And he started looking for different, many solutions satisfying this property that all the solutions follow the same path. So basically, Carles Simon, he found thousands of solutions having this property, and then he coined the name of choreographic solutions. So choreographic solutions are solutions of this sort, where all the particles follow the same path. So that's where the name of choreography was born. Next slide. So this is, well, this was supposed to be an animation of the figure 8 choreography, but we're going to see it later. So the figure 8 choreography is going to follow an 8 solution. Here we're seeing a starting configuration where all the particles are on a straight line, right? And well, I mean, for the people who have seen the figure 8 choreography, they know more or less how it looks like. Later, we're going to see the figure 8 solution, right? So, and actually, I have there a link to a Scholarpedia webpage where people can see the actual animation working. Next slide. Well, yeah, you can see the figure 8 choreography there. Yeah, thanks a lot, Tiago. We could go back to the presentation and the next slide. Okay, so the variational methods used by Schanziner and Montgomery, they gave rise to different techniques using variational techniques. So the main problem of variational techniques is basically avoiding collisions, right? So there was a clever argument introduced by Marchal, where you can get estimates that avoid these colliding configurations. We're going to talk about Chris Marchal later in the talk, but then there was some works done in that direction, and after that there was a plethora of different works using the same variational techniques. I mentioned here some of the names of the people who have worked on this, and this is an industry that's still going on. People still use this kind of technology in order to prove the existence of choreographic solutions and different kind of solutions for that matter. So then that's why I put 3 dots, because there's this is a partial list, and then there's many other people who had contributed to this this technology. So we can go to the next slide. So so here I'm going to be talking about a different technology, which is something else that we have been doing, and it's based in a work of Schanziner and Feijós, and basically we use the idea of continuation methods. So we start from a known solution. In this case, we start from a polygonal solution for the embodied equations in the rotating frame, and then using continuation arguments. For instance, Schanziner and Feijós were using the Weinstein-Moser theorem, right? And they proved that for particles less than 7, there's branches of solutions that come out of the equilibrium configuration. So down there, I'm showing the equilibrium configuration for 4 bodies. So the 4 bodies are in a square or rhomboid, if you want, and then there's families of periodic orbits coming out of that configuration, right? And these are called Lyapunov families. So it was an observation of Shensinor and Fayos that along these branches of continuation, there's an infinite number of choreographies that exist. They're actually dense along the branch, and these choreographies can be characterized by several characteristics of symmetry and so on. And we can go to the next slide. Okay, so here I'm showing the equations of motion to the n-body problem in the rotating frame. So this is based on a work that was done by Jorge Ise and Carlos García-Azpeitia in Mexico, here at UNAM. So they basically used equivariant degree theory to show that, well, first that, so you have all these equilibrium configurations that I'm showing down there. So for the equations of motions in the rotating frame with a very special frequency, right? You have that the polygonal solutions are relative equilibria for the equations of motion in the rotating frame. Okay, and then from these solutions, one tries to find branches of Lyapunov solutions that come out of those equilibrium configurations. And then the next slide. So here's the thing. So you have to adjust. So you have to adjust the frequency of the rotating frame, right? So the frequency equal to square root of S1, and S1 is an explicit expression that appeared on the previous slide. So if you set the frequency to be this, and then you can find, well, basically the expressions for Wj are relative equilibria for the equations of motion in the rotating frame. So you have equilibrium configurations, and then in the next slide we're going to see a theorem by. Could we go to the next slide? Okay, so you can get a theorem about branches of solutions in the vertical direction. So in order to do that, Jorge Ise and Carlos García-Azpeitia were using equivariant degree theory, and in equivariant degree theory you have to take into account the symmetries of the problem. So what are the symmetries of the problem for the equations of motion in the rotating frame? Well, basically you inherit symmetries that come from the equations of the n-body problem. So you inherit rotations in the xy plane, right? You have a change of phase in time, and then you have the symmetry of translations in the z component, right? I'm showing here. I was supposed to point at the symmetries in the figure on the right, but I'm hoping that you can imagine them without me pointing to them directly. So then you can get a theorem that I'm thinking that it's in the next slide. Okay, so here's the theorem. So this was a theorem that was basically related to the work of Carlos García-Azpeitia for his PhD dissertation with Jorge Ise here at IIMAS. So the thing is that for particles greater than or equal to 3, you can find different branches of solutions coming out of the polygonal relative equilibrium, and you have different numbers that go from 1 to n/2, right? And then you have branches of solutions, of periodic solutions that come out, which are basically Lyapunov solutions, and the Lyapunov solutions have starting frequencies that are given by explicit expressions given by square root of sk. Okay, this number k also plays a role in the symmetries of the problem. So you have the symmetries of the problem are given in the expressions that I show here on the theorem. We have expressions for w. W is a complex number, so that represents the xy component. So there's a symmetry in the xy component. There's also a symmetry in the z component. Okay, and then we can see the symmetry expressed in the next slide. I think we can skip the next slide because it's an animation that's not going to show up. But in the following slide, yes, here I show the symmetry for the case of 4 particles. So we start from 4 particles. The relative equilibrium is a square. It's on the xy plane, and now there's branches of solutions that come out, and the branches of solutions are expressed in this with these expressions that they basically involve delays. So if we look at the equation for Wj, we see that the expression for Wj is basically a rotation by 2 pi over n. N is the number of bodies, so it's 2 pi over 4. So it's a rotation by 90 degrees, right? And then the solution is an instance of the previous solution, but with a delayed term t minus j k zeta, right? So that means that, for instance, what I'm showing there in the picture is that one of the particles, for instance, lives on a solution that's a figure-8 solution. Well, then the next particle is going to be a rotation by 90 degrees, and the particle is going to be at some instance on the curve that's delayed by a time of, in this case, pi, right? So if one particle, let's say the red particle, is at the bottom of the curve, the next particle is at the top of the curve, right? And that is related to the fact that this branch corresponds to the number k equal to 2. But remember, we have different branches for different numbers, and for those branches, the particles are going to be showing at different different instances. So the symmetries are going to be different, and there's a symmetry also for the set component. So then on the next slide, we show how to characterize choreographies from these branches that we obtain. So first, we show the branches that come out of the theorem, right? We have 2 expressions. The first one, the expression for W is the xy component of the particle, and then the z component is downstairs. So now if we're looking for choreographic solutions, so we're looking for solutions where all the particles follow the same curve, right? So we start from a solution along the branch, and then we transform to the inertial frame. That's the equation for U, right? So we want to get rid of this rotation that appears in front of the equation for UN. How do we get rid of that rotation? Basically by choosing the frequency. Okay, so we want to get rid of that frequency term in order so that all the particles are following the same curve. So on the next slide, we show how to get rid of this frequency. Well, basically, you can get rid of the frequency by having integers that satisfy a Diophantine equation that's downstairs. So you have integers L and M, which are relatively prime, such that the expression is satisfied. Then the rotation term disappears, and all the particles are following the same path, which is the path of the equation of the particle UN, the last particle, let's say, and the particles are going to be appearing at different instances of time. So this is the equation for a choreographic solution, and this is only for the XY component. So we have to do the same for the Z component, which is on the next slide, but the idea is basically the same. for the set component, you don't have this rotation term. So basically, you figure out that by doing this, satisfying this Diophantine equation, you basically have a choreographic solution, let's say, right? So this is in fact a fact of life. So we have a theorem, which is on the next slide, that says So before the theorem, so we have that. So let's say this Diophantine equation is satisfied for numbers L and M, which are relatively prime along the branch. So we're going to call these orbits along this branch that are resonant orbits. They're resonant orbits because the frequency corresponds to multiples of the time and frequency, which are multiples of these numbers L over N, which are integers, right? So that's, in that sense, they're resonant. And of course, they have to satisfy the bottom equation that Tiago is showing, which is that L, M, and K, they have to be, in that sense, K times L minus M. They have to be an integer, which is a multiple of N. So if all of that happens, then we have a resonant orbit, and the orbit is going to be a choreography solution. Okay? So then in the next slide, we actually state the theorem, that is that if the resonance conditions are satisfied, then we have a solution that is a choreography. And the choreography is going to be characterized, and we say something about the characterization on the next slide. So we have two numbers. We have two numbers L and M. So if you look at the choreographies that you obtain by satisfying this Diophantine equation, you have that the choreographies that show, when projected on the XY plane, they have a symmetry of rotations by angles 2 pi over m, and there's a winding number which coincides with the number L. So the projected curve winds L times around the origin, and it has a symmetry of rotation of 2 pi over m, right? So that's the relation between the resonant period and the choreography, okay? So this is a theorem that we proved, well, actually, based on the work of Ise and Carlos García-Azpeitia, we proved it for the n-body problem. But in the next slide, we show that we also have proofs of the same theorem for the case of the point vortices equation. And this is something that I wanted to mention. We had numerical computations, and we extract also choreographies in that case of the n-body problem. And this is related to some work that Hildeberto Cabral also did for the n-body problem. We have the same thing. We have Lyapunov families that come out of equilibrium configurations, and these are point vortices on the sphere. And I'm putting there the related work of Hildeberto Cabral. And you can also find choreographies along these branches of solutions. Okay, so the next couple of slides are basically well, they were animations, but they're not going to show up, so there's no point in looking at them. So I was basically showing the branches of solutions that come out. So the branches of solutions, they basically, you can see how the branches of solutions come out. You can also see them, these animations on my webpage, but there's no point in going there now. So I want to talk about computer-assisted proofs. And to do that, we started looking at a DDE framework. So like I said before, from the theorem of Jorge Ise and Carlos García-Azpeitia, basically you obtain symmetries that are given in terms of delayed terms, right? So if you take the equations of the n-body problem, which is the top equation there in the rotating frame, and you impose the symmetries that these solution branches have when they come out of the equilibrium configurations, then you obtain a delay differential equation. So here, what I have, this operator G is a delay differential operator that's defined in spaces of, if we're looking for periodic solutions, they're defined on spaces of 2π periodic functions, right? Which are going to be characterized in terms of Fourier coefficients. So then, if we're looking for periodic solutions, we basically need to find periodic solutions that are zeros of the operator G for a given frequency number, right? So this is our goal, finding zeros to this operator right here, and that amounts to having periodic solutions. And basically, on the next slide, we can see that this equation has also symmetries, which are the symmetries that were inherited from the n-body equations and that are preserved in the rotating frame. So we have three symmetries that I mentioned before, which are rotations in the xy plane. So if you have a solution and then you rotate it in the xy plane, you also obtain a solution. If you change the phase, which I'm showing there, you also obtain a new solution, right? So if you change the phase, that's also a solution. And if you translate the solutions in the set direction, you obtain also a different solution. So all this is summarized in the equation at the bottom, which is basically saying that you have three parameters that account for theta accounts for rotations in the xy plane, phi accounts for changes in phase, and tau accounts for translations in the set component. Okay, so we have three parameters, right? And the equations are basically invariant under these group actions, which is showed in the next equation. So what do you do? Sorry, in the next slide. So what do you do when you have invariance under these group actions? Well, basically, you can obtain zeros of the equation by augmenting the equation with Lagrange multipliers. So you have three parameters, which are account for the three group actions. So then you have to add three different Lagrange multipliers, and the Lagrange multipliers are going to be multiplied times the three generator fields of the three symmetries. So we have here at the bottom we have 1, 2, and 3. The first one is the generator for the rotations in the plane, right? Second one is the generator for changes in the phase. And the third one is the generator for translations in the set component. Okay, so now you have an augmented equation. You go to the next slide. And in the next slide, you realize that since you added three more parameters, you have more parameters than equations. So you have to add three more equations, and you add the three more equations basically by adding Poincare sections. The Poincare sections, they're going to be acting on the three group actions, right? So you have equation 1 is the Poincare section for the rotations in the plane. Equation 2 is the Poincare section, well, the usual Poincare section, which is going to fix the phase. And equation 3 is going to be the Poincare section that tells, well, I put a 4, but it's supposed to be a 3. Sorry about that. So that's the Poincare section that fixes the translations in the set component. Okay. Now, on the next slide, so we show the equations for this delay differential equation. And now there's something I want to point out. On the second equation, the sum term, that amounts for the potential. Sorry, for the gravitational the gravitational attraction force. So that force, as everybody here knows, is a force that's given by the norm sorry, a vector over the norm cubed of the vector. So in order to get computer-assisted proofs, we wanted to have, it's not completely necessary, but we wanted to have a polynomial delay differential equation. So so one realizes that this potential 1 over the cubed of the norm satisfies a polynomial differential equation. So you can basically change that equation into a polynomial differential equation by augmenting the equations of W, which are the equations, the differential equations that this potential satisfies, right? So if you do that, you augment the system, but then what you have is a polynomial delay differential equation. I was going to say vector field, but this is not really a vector field. It's a delay differential equation. You also have to augment initial conditions, which is what I'm showing at the bottom, right? But once you have this on the next slide, you can basically start looking for solutions to this delay differential equation by looking for periodic solutions in a Banach space of periodic solutions, which is characterized by the Fourier coefficients, right? So this is actually a Banach algebra if you take into account the product or the convolution, the discrete convolution operator. So you're going to be working on these spaces of periodic solutions, and on those spaces of periodic solutions, basically, you need to look for zeros of this Fourier map. So this Fourier map is a map that has many components, and the components basically amount for the Poincaré sections that you added to the equation, the appended initial conditions, and the two bottom equations G and H, which are basically your delay differential operator and your appended equations. So this is the map that you have to find solutions to, and this is what you're going to work with. So we can go to the next slide, and here I'm basically showing a Newton-Kantorowicz kind of theorem, which is, well, basically a theorem that tells you that if you have some estimates, which are the estimates that I show here, this y0, z0, z1, z2 times r, if those estimates are satisfied, then you know that if you have an approximate solution, so you have a solution that satisfies the equations that I showed before very approximately, and the bounds are satisfied, then the theorem tells you that this approximate solution is in the basin of attraction of a Newton iteration, and the Newton iteration converges to a real solution. So you turn this into a computer-assisted proof by saying, okay, I have an approximate solution. I evaluate to this approximate solution all the bounds that I'm showing here rigorously, right? If that is satisfied, then it means that close by there is a true solution in the Banach space. So this is a computer-assisted proof because using the computer, you check that the bounds are working appropriately. And if that happens, then there is a true solution, and you know that this is an exact solution of the delay differential equation, and that is going to be a periodic solution of the n-body problem. Okay, so this is, let me say something about this this theorem. So this is the technology that my collaborators, Jean-Philippe Lessard and Jason Mireles James, have been using for a number of years, and basically they started collaborating with us in order to implement this thing for this kind of theorem for the delay differential equations that we obtain in order to follow the branches. And they also came to Mexico to give courses on how to use this technology, and then people are using this technology right here. So on the next slide, I show the different approaches to the same kind of problem. There's the work of or mainly Polish people that are in Krakow, the CAPD numerical software. Of course, Carlos Simó is not in Krakow, but he collaborated with them. And then this is software that uses interval arithmetic, and then with that interval arithmetic, people like Thomas Capella, Carlos Simó, Piotr Skliczynski, they were able to obtain computer-assisted proofs of choreographies, existence of choreographies. For instance, the works that I'm showing, the Capella-Simó 07 and Capella-Simó 17. These works are related to the existence of the figure 8 using computer-assisted proofs and the stability of the figure 8. So they proved using computer-assisted methods that the figure 8 choreography is a stable solution, stable in the sense of KM theory. So due to the dimensions, it's not well, there's Arnold diffusion and so on, but it's at least KM stable. So the spectrum is so that you have a Birkhoff normal form around it. Okay, so there's also the work that I'm showing here, Gianni Arioli, Divina Barutello, and Susanna Terracini. They used a functional analytic method, which is close to what we're using here, but they were using vector fields instead of delayed differential equation. And let me emphasize this. It's also the case for the CAPD methods. They're all done for vector fields, and when you work with vector fields, you know that the n-body problems for vector fields is always a 6n dimensional equation where n is number of bodies. So the dimension of the problem grows very quickly, right? In our case, since we were using delay differential equations, we only care about an equation for one of the particles. This one particle, and one particle basically amounts for the particles of all the other particles, because they're all related by symmetry, and that's the meaning of the delayed differential equation. So our methods, they only use 6 plus n-1 dimensions, which is a dimension that's a lot less than the 6n that you would obtain with the vector fields, right? So doing exactly what I described before. On the next slide, you can see some of the figures, some of the pictures that we found. So here I'm showing some choreographies. The one on the top is the trefoil with 5 bodies. So we basically proved computer-assisted, right? That this is in fact a choreography. This is a spatial choreography. That's why I'm showing, let's say, 2 views of the same choreographies. And then you can find other choreographies, which are, well, we call them torus knots, because these choreographies that we found are basically torus knots that are showing up in along these branches of solutions. Well, they appear after a bifurcation that were in an animation that I couldn't show, but maybe you all have seen those animations or can see them in my webpage after the talk. And in the next slide, I show more choreographies. I show a choreography with a torus knot with 7 bodies, right? So the figures on the left are basically the choreography in the rotating frame, and then on the right, the 2 frames on the right are the choreographies in the inertial frame. So the top is a choreography with 7 bodies, and the bottom is a choreography with 9 bodies. Okay. So on the next slide, I start talking about well, there was a conjecture by Marchal. So Marchal basically realized that there's a branch coming out of the triangle. This is in the inertial frame, as was pointed out by Alain Sinner to me. So there's a family that's called the P12 that has 12 symmetries that the figure eight has, right? So then Marchal thought that this branch of solutions coming out of the circle basically ends in the figure eight choreography, right? So he immediately conjectured that. And then on the next slide, so we have, so there was on top, we see Marchal's conjecture. In the inertial frame, the circular choreography is connected with the figure eight solution. Okay, so we rephrase, let's say, Marchal's conjecture in the rotating frame context. So basically, in the rotating frame, if you transform the circle or the triangle, the triangular configuration to the rotating frame, you have a regular equilibrium, and there in the rotating frame you have a branch of solutions that that could connect in the rotating frame to the figure eight via continuation. So that's what I'm stating down there, that there's a continuum of periodic solutions from the triangle in the rotating frame to the figure eight in the rotating frame. So in the next slide, I'm showing some work that we did some years ago with Eusebius Doedel. This was numerical work. And then we found, and there was supposed to be an animation there that doesn't show up here. So basically, we found that there was a connection in the case of 7 bodies. So we have the configuration with 7 bodies down there in the left panel, right? We have a branch of solutions that come out. There's a bifurcation where the solutions, well, the solutions there, they first show up in the shape of small eights. They start growing. At some point, they have a bifurcation where there's a symmetry breaking bifurcation where we have solutions which have axial symmetry, and when the solutions with axial symmetry meet at the origin in the rotating frame, that corresponds to the figure eight solution, which is the green dot at the end of the continuation, right? So we knew that for the case of 7 bodies, so we knew that there was some connection in the rotating frame from the polygon, in this case the heptagon, all the way to the figure eight, and there was a bifurcation in the middle, and then this bifurcation basically changed the symmetry of the solutions. So in the next slide, we actually did some numerical work for the case of 3 bodies, and then discovered that the same case happens for the case of 3 bodies. Now, the case of 3 bodies is is a lot more difficult because the triangle is very degenerate. So the degeneracy of the equilibrium configuration is order 5, right? So you have this Hamiltonian. So you have 10 directions in the kernel, but at some point, so we have all the description in the paper that appeared this year in celestial mechanics and dynamical astronomy. So we were able to come out of this triangular configuration. We follow a branch of solutions. This branch has a bifurcation, which happens. It goes in the same way as in the case of 7 bodies. There is a symmetry breaking bifurcation. You have orbits that have axial symmetry that come out, and then those orbits end up meeting at the origin. When they meet at the origin, it's the green dot that we have there. You transform to the inertial frame, and you have the 8. So there's a connection in the rotating frame from the circle to the figure 8. And then there's some animation that I was not able to show, but on the next slide I show that the same thing happens for a different number of particles, right? We already knew it for 7 particles, right? So we found it for the case of 3 particles, which is the 3-body problem. It's related to what Marchal was saying in the inertial case. But we also found that it works for the case of 5 and 9 bodies and different odd number of bodies. The thing is that what you discover is that along these branches, there's many bifurcations, right? Well, here I'm showing in this slide, I put the bifurcations by dots. There's, of course, the symmetry breaking bifurcation, which is the blue dot that I showed before. But you see that the Morse index changes many times along the branches. So there's many bifurcations along these branches, and these bifurcations, they change the stability. And this is something that I should mention, that this is something that you can see in the equations of the n-body problem. But when you translate the equations to a delayed differential equation, you're imposing a symmetry. So you're getting rid of many of these bifurcations. In fact, the only bifurcation that you observe, that we were able to observe in the delayed differential equation, is the blue dot. All the others, in order to find them, we have to explore the what do you call it? Well, we have to explore the n-body, the vector field, the n-body problem equations. Okay. On the next slide. So we have connections from different polygons all the way to the 8, and it happens for a different number of particles. And we know that, for instance, as we saw on the previous slide, we know that the 8 is stable, right? So there's a small interval, of stability along this branch, and but that's not the case for a different number of particles. So here I'm showing the continuation for the case of 15 particles. We start from a polygon of 15 with 15 particles. We follow the branch. We go through a bifurcation, which is the blue dot, and then a second branch that ends in the green dot, that is the 8 with 15 bodies. So this is a prototypical example that happens with different number of particles, and we were able to do that continuation for odd number of bodies from the case of 3 particles all the way to 15 particles, right? And there was an animation there, but you can see basically the figure. You can see 2 instances of or 2 views of the choreography that one obtains, which is one of the intermediate choreographies that show up along this branch. So these branches are going to be densely covered with choreographies. There's infinitely many of them, and I'm showing one of them, which is easy to see. Okay, well, on the next particle, on the next slide, I'm showing the continuation for the case of no, the previous slide. There was a slide in the middle. Can we go to the previous slide? Previous, before. Okay, yes, this one. No, the next one. No, next slide. Next slide. Yeah, this slide. So here I'm showing the continuation for the case of 3 bodies. So we start from a circle. We undergo a symmetry breaking bifurcation, right? And then we go along the last branch before arriving to the 8. And you see different changes in the Morse index. So here, these numbers that I'm showing are the Morse indices, right? And you see that right before arriving to the green dot, there's the Morse index is 0, which means that all the solutions on this interval that's labeled with 0 are stable. And along this interval, you can find different choreographies. And I'm showing one of the choreographies that is inside there. So what I'm showing there is a choreography. It's a choreography that's that is stable because it's in that last interval. So we have a stable choreography with 3 bodies, and it's a spatial choreography. And so we were happy to find that because we found a stable spatial choreography. Well, stable in the same sense as the figure 8. So it's Km stable. So you have a Birkhoff normal form around it. which means that this thing is going to be more or less stable. So there was an animation, but well, actually, this animation you can actually find it in my webpage, and there's a link at the end of the talk where you can, it's even down there. So down there in the link, you can find an animation to this choreography. So let's move on to the next slide, which basically sums up what I was telling about before. So we have odd number of particles going from 3 to 15. Well, 3 to 15 is the numerical work that we could do. We're thinking that the same phenomenon happens for different odd number of particles. So here I'm showing the figures in the bottom. Is the first one is the case of 3 particles, then 5, 7, 9, 11, and 13 particles, and so on. We did it up to the case of 15 particles, and the same thing, basically, the same thing is happening. So you start from a polygon with 3, 5, 7, etc. number of bodies, and all of those end after one bifurcation for the delayed differential equation, right? Because the n-body problem has more bifurcations. They all end up in the figure 8 with an odd number of bodies, right? Okay, so the next slide is basically a summary of what I've presented here. So, so I described how to do well, computer-assisted proofs for the existence of choreographies along these branches of solutions that are, I know these are very special branches of solutions because they have some symmetries and they all come out of these polygons. But other than that, this method is systematic, right? It's a functional analytic approach to computer-assisted proofs, and everything is done in Banach algebras, right, of periodic solutions, and also by doing this and then exploring the stability of these solutions, we were able to find a stable choreography with 3 bodies, which is spatial choreography. And well, we still don't have a computer-assisted proof of the whole continuation from the polygons to the figure 8, but we can do computer-assisted proofs of the branches, the choreographies in the middle. And basically, when you have a computer-assisted proof like this, what you obtain is an infinite number of choreographies because you obtain, well, you basically prove the existence of a small interval along the branch, right? So you have an infinite number of choreographies which are inside that interval, even though most choreographies are not going to be very interesting, you can still find all of them inside, right? And well, and that's basically what we found. So I do want to mention that we still do not have a computer-assisted proof of the whole continuation because there's something that we're missing, which is that we need to find computer-assisted proofs for the bifurcating branches. We can do the branches in the middle from bifurcation to bifurcation, but in order to have computer-assisted proofs of the bifurcations, let's say coming out of the circle and then passing the bifurcation that has axial symmetry, we still have to do a little bit more work. There's some work by Jean-Philippe Lessard and J.B. Vandenberg, where they do actually prove computer-assisted that the bifurcations are in fact true, and then we're using that in order to extend our results. So the next slide is basically is the last slide, to thank you all for your attention and to wish Hildeberto a happy birthday, and I'm showing also the references of the work that I presented today, and then there you can also find a link to the animations that I couldn't show here, but they're on my webpage. So that's not too bad, and thanks to Tiago for passing the slides for me. And I would be happy to take any questions you might have.
thank you, Renato, for your nice presentation. It's a very big and it's a very big project, and with a lot of interesting results. It's a it was a nice talk. Then we pass for the questions, and someone have some question.
Yes, I have a question. Could you explain the relation between the family you have between the Lagrange solution and the 8 and the Marchal P12 family? Obviously, they are not the same. There is no bifurcation in the P12 family. I don't think your families are the most natural between the polygon and the 8.
Renato, do you listen the question? Only for check, because I'm not sure if are you listening me.
My question is the relation between your family connecting the Lagrange equilateral triangle solution to the 8 solution with the P12 family, which has no bifurcation, and which in the rotating form has always the same symmetry.
I'm sorry, Alan. I'm not sure if Renato can hear us.
I could hear a little bit, but the audio is very bad, so I cannot understand the question.
I understand. Annette, maybe we can tip the question, no?
Well, maybe I write a message to Renato.
It's better.
Anyone have another question? Maybe it's better to tip the question.
Renato, can you hear me?
Yes.
Oh, good. So I wanted to ask you about the calculations on the Morse indices you had on those branches, and in particular, which Morse indices are you calculating for those branches of periodic solutions coming out of the polygon solutions?
Well, basically, it's very simple, Dan. So we had. So let me say it this way. So we have the branches that we continued with the delay differential equation. So we take those solutions and we go back to the equations of the n-body problem, right? And there we basically just write down the variational equations and we look at the spectrum, right? So basically, the Morse indices here are going to be the number of stable eigenvalues, right? So the eigenvalues that are away from the unit circle. So that's what we're showing. So then, what I was showing before, the Morse index 0 is basically that all the eigenvalues are inside the unit circle. So that's what we're showing.
Okay, I see.
Renato, Alan Chasney write the question for you in the chat. Can you see the the question?
Okay, yes. So Alan's question is that the relation between the families that we find and P12, which has no bifurcation and shares always the same symmetry in the rotating frame. So, so thanks for the question. I'm not really sure. I was thinking about this since the last time we met. The thing is that so it's very nice that Thiago is showing this slide precisely here, right? Because the thing is that we know that the 8 is stable. So I'm thinking at least one bifurcation has to happen between the circle and the figure 8, because if the circle is unstable and the figure 8 is stable, then there has to be some kind of bifurcation in the middle. So what I'm guessing is that P12 maybe doesn't have a symmetry breaking bifurcation like the blue dot we find here.
But the circle is not stable for equal masses.
It's unstable, yes. The circle is unstable, but the figure 8 is stable. So there should be some bifurcation in the middle, even if it's not a symmetry breaking bifurcation, because actually the continuation from the whole branch P12, I've seen the animation that Jacques has on his webpage, and basically it preserves the symmetries along the way. So there's no bifurcation in that sense.
Yes.
In there. But there should be some.
In your family, there is a bifurcation of the symmetry, isn't it?
Well, there's a bifurcation when the circle opens into something. But that's I don't think that's the bifurcation that where the family becomes stable. I think the bifurcation should happen later.
Yeah, I don't understand the relation. I don't think it's the same thing.
No, it's not the same thing. But what I'm saying is that there should be some bifurcation where the branch at some point becomes stable, because if it ends on a stable choreography, the 8 is stable, and it's not stable before, there should be a bifurcation in the middle. Do I explain myself a little bit?
Yeah, I should. It's a long time. I didn't think to this. I should look again. But it looks. Your diagram looks strange to me.
Yes, to me it's also very strange, because I'm expecting something to bifurcate in the middle, even if it's not. Well, this slide that Thiago is showing. So the bifurcation that where the branch becomes stable is not a symmetry breaking bifurcation. It shows up along the same branch, right? So it's almost like it shows up unnoticed, right? It's just we look at the spectrum and then we see numerically, right? Numerically, we see that the eigenvalues enter the unit circle, and that's it. And then the solutions become stable from there on, and then we find other stable choreographies. But something like that has to happen in the P12 family, because at some point the solutions become stable.
Renato, I have a question.
Among all possible solutions, not among a given symmetry class. I suppose this is all.
Renato, it's a numerical work, right? And I don't know the numerical details, but there is the possibility that in this bifurcation, the branches to be very close, but still a different branch, or this is a true bifurcation.
You're talking about the blue dots?
In here, there is this branch, there is another branch, and the bifurcation. But my question is, you have shown that this is a true bifurcation. Let me try to explain. You exclude the possibility that these two branches are different, but very close each other, but different.
Well, yeah, the two branches are different. They so the two branches of solutions, they basically coincide in this bifurcating solution, which is the blue dot, right?
Okay.
And that blue dot is what I was saying, that it's a symmetry breaking bifurcation. So I can tell you that this vertical line are all solutions that have they look like little 8s for each particle, right? So you have 3 little 8s for each particle. The amplitude increases. At some point, there's a bifurcation, and these 8s, they break and they open up, and they become circles, right? And then on the horizontal branch, you're going to have solutions that basically look like circles that do not meet in the middle, right? So that's how this symmetry breaking bifurcation happens, right? And it turns out that those circles, there are 3 circles that end up colliding in the origin. When they collide, that is the figure 8 solution in the rotating frame, right? So then you pass through this solution, the figure 8 solution, right?
Okay, another question. There is breaking symmetry bifurcation, and
Yes.
for sure there is bifurcation where the symmetry is not broken, right?
Yes.
There is, some criterion, a partial criterion, criterion to decide if the bifurcation is. Do you know some criterion to decide if the bifurcation broke or do not broke the symmetry?
Well, Tiago, it's a good question, because actually, first we did the numerical continuation, and the numerical continuation was done using the DDE. And the fact is that in the DDE, you don't see these other bifurcations that are not symmetry breaking, right? For instance, in that slide that you're showing there, you only see the blue dots, right? The other ones, you don't even notice. It's only until you take those solutions and then you look at them in the equations of the n-body problem that you realize that there's a bifurcation. So the thing is that it turns out that the way you construct the DDE, you're imposing the symmetries that come out of the theorem of Ise and García-Azpeitia. So that is given, and you put it in the equations, and those equations, they're solutions that only satisfy those symmetries, right? So So we're guessing that you go through the continuation and you don't see those other bifurcations, because those bifurcations, they might break something else that is not related to the symmetry of these branches, right? So talking about a criterion, we don't have any criteria, but we're thinking that those other bifurcations are not related to the symmetry that is already imposed in these branches. So it's something else. It's something else. So maybe they have to do some other symmetry that is not important for the symmetries that we impose in the delay differential equation. But in fact, the blue bifurcation, the blue dot that we see here, this is fundamental for the symmetries, because you can see the symmetries of the problem. One of the symmetries is broken, which is the fact that, as I was saying before, we go from solutions looking like small eights to solutions looking like circles like this, opening up. So yeah, so there could be a criterion. We haven't looked at this in detail, but there should be something related to the shape of the equations, maybe in a phase space or something.
A last question. At some point, I like a little bit algebraic geometry. Then I have some interesting in the following question.
Yes.
There is algebraic choreographies in this sense. The choreographies are in algebraic curve. You see,
yeah.
The circle is an algebraic curve, but you working S1. But if you impose that, if you how this is the question. There is choreographies, algebraic choreographies. Algebraic choreographies for me is the curves are in a algebraic curve, or in general algebraic surface. And if there is choreographies of this type, maybe it's possible to use equivariant algebraic geometry to determine those choreographies. I don't know, but because if the curve have some symmetry, the choreography will have some symmetry also, and Chancellor in some weeks ago said that all node choreographies are non-algebraic. Then I'm with this question in my mind.
Well, yes, there's also the work of Fujiwara, where he basically wants to find the equations that have the lemniscate as an algebraic curve, right? The lemniscate as a choreography, and then he finds a potential that I don't remember exactly what is the potential, but his paper, he finds a potential so that you have equations so that the lemniscate is a choreography, right? But then, so I don't know. You could start from there. It's actually also I talked to Professor Fujiwara, and then he basically well he asked me something related to that. So could you do the same thing with different potentials, and maybe you could try some potentials that have algebraic curves as choreographies, right? Like that example of the lemniscate. But then all the rest is the same. So basically, everything that I showed, it works more or less the same if you change the potential. So if you put a potential that has an algebraic curve as a choreography, basically all the same. You can, for the symmetries, you can have the equivariant degree theory and find the branches and so on, and repeat everything that we've done here. Right?
Okay, okay. Thank you, Renato, for the nice talk and for answering the questions. Someone have another questions?
Okay, let me ask you a question. Your bifurcation parameters, the omega is, what exactly is omega? That's the frequency?
Yeah, omega is the frequency, right? So in order to bifurcate, you have to start moving the frequency, and then you continue the solutions
right.
like that. Yeah.
So your vertical line is basically that the Lagrangian for the three-body problem, right? And then the more horizontal line is the figure eight. Kind of the branching curve coming from figure eight. So for the figure eight solution, if you change the frequency, so what do you get? You no longer get figure eight, right? It's a three independent path. So what you get is a three independent path, which is close to figure eight, but three different paths.
Yes. For instance, maybe Tiago can show maybe the next slide, the one after. It's the one after. I think this is related to your question. So there you can see the green dot is the figure eight, right?
Right.
You move a little bit along this branch. So the previous arrow, right, that's a choreography along this same branch, which is not exactly the figure eight. So this is a choreography with a slightly different frequency, right? Which in the rotating frame, it looks more or less like a solution that's close by. But in the inertial frame, what you see is that choreography that Tiago is showing right there, right? So it's like it's a figure eight that is rotating very slowly like this, right? And that's what you see.
Yeah, I see that picture. So it's basically when you do minimization, you change the time when you reach the minimization. So the parameter, this is a parameter you obtained.
Yes, that's correct.
So the symmetry breaking bifurcation at that point, what's happening at that point?
At the symmetry breaking bifurcation, well, basically, at the symmetry breaking bifurcation, well, you have another branch with a different symmetry that emerges from that. So you're changing the frequency, and then you could continue that same branch, and that branch is going to continue. So these branches are global in the sense of Rabinowitz, right? So they only end when you go through a bifurcation, or the norm goes to infinity, or the period goes to infinity, right? So this is basically what happens. There you could continue the branch and then see where it goes. Maybe it goes to a collision or something, but at that point you have a bifurcation. So in the kernel you have an extra direction, and then follow it, and it's
yeah, I understand. So but correspond to the Lagrangian, which where is this happening? What frequency or what Lagrangian orbit correspond to this bifurcation value?
Also, so in terms of the Lagrangian, so we haven't.
Right. So you have vertical line, almost vertical line. So at which point that you actually start to see that? When does the symmetry break?
Well, I could tell you the point, but I don't think it has anything. At least we didn't find anything particular about the point where this bifurcates. So We didn't look at the Lagrangian, that's true, but the frequency, it doesn't seem to be special at all.
That frequency, so let's say for three-body problem, that we don't, so that point one, that point, of bifurcation point, there's no physical importance or any explanation why it happens at that point.
We couldn't find any. There might be, but we couldn't find it.
Okay, that's interesting.
It doesn't look special from the computations that we did.
Physics, from mechanics, or anything. There's nothing special.
No, that we know of. No.
That's quite interesting. Thank you.
Thank you.
Thank you, Professor Xia. Someone has another question or comment? If no, I would like to thank you. There is some. If someone have question or is a problem with microphone? Someone have problem with microphone? I don't know. If anyone have questions, I would like to thank Professor Renato again, and thank you, Renato.
Thank you very much for the invitation. Thanks for being here. Sorry about this.